anyone inside the campus. Well, if it's outside the building, it's fine. As long as you're inside the building, you have to wear a mask.
Okay, okay. And there is a complication of this mask now. So mucormycosis is coming because of mask and then post-COVID situations. Fungal infection. Yeah, we are having that black fungus, mucormycosis. So that's a big concern in India. And in India, its situation is very bad now.
Yes, I know. I know many of my, I'm in sort of 3 or 4 WhatsApp groups with people I graduated from my college, and also from my high school and middle school. And there are quite a few of my classmates that have gone through COVID.
Oh, yeah.
And quite a few, meaning of the order of, I would say 30 to 40%.
Okay.
Between them and their spouses, they have gone through COVID. And then I think few people may have passed away. I can only recall 2 or 3. I can only recall 3.
Yeah, actually this time what we are telling is right. So we are seeing the persons dying. We know very well the well-known persons to each other. And also in WhatsApp group, every day or other day, we are getting someone is dead, like in our WhatsApp groups. Many groups are there, no? Our high school group or something, graduation group or something, master's group and a PhD group like that. So in many groups, every day, I think 1 or 2 deaths is occurring in India.
Yeah, I mean, I know it's pretty bad. Here it was that bad only in New York some time ago, which was like last June, more than a year ago. But now it appears to be better, and they're pushing vaccinations and so forth. I have been vaccinated twice since late March, was my second vaccine.
Okay.
But we're also, the university is also not enforcing. They cannot really enforce. Here there is some sort of liberty. You can do whatever you want. So they tell us to get COVID tests. So my COVID test is supposed to be next week.
Okay.
Every 2-3 months, I think they will make everyone, certainly employees, to have COVID tests done.
Yeah, here also they are doing a lot of COVID tests, but the population is huge in India. It's a very big concern.
Yes, yeah, I know.
138 crore population. It's very difficult to vaccinate everyone, and it will take some time to vaccinate everyone in our country. Just now, I think from 25th onward, they are starting for above 18 years.
I see.
But the efficacy of the vaccination, they tell 80% that Covaxin and Covishield, and 99% are not getting infected, but 0.0%, 4% are getting infected. So even after taking the vaccine, but they are very less in number. 0.04 means out of 10,000, 4 people is not a big number.
Yeah.
Yeah, and also out of 4, all will not have any symptoms. They may be asymptomatic also.
Sure.
Yeah. That's what actually happening. And what we are actually hoping that the current situation may soon be completely over. We pray the God. We cannot say that it will be over. Third wave is also there. They're telling in August, September. So in the third wave, the main people who are getting infected is children. They're telling. So first wave above 60 years. Second wave like between 30 to 45 years. Second wave. Third wave is around above 18 years. Children, they are getting infected. They are telling they'll get infected.
It's the same situation here. Most of the infections are now with younger people.
Yeah. And because of this, our labs are closed everywhere in most of the institutions in India. I don't know the situation in abroad, but students are now not working in their labs. Only simulation they are doing, not work. Physically, they are not there in the lab. So we cannot do any experimental work.
Here the labs, at least in this university, labs are open, but you have to get special permission to be there. Most of the time they give it.
Okay.
So it's kind of So I would say it has been open except for the first 2-3 months after March 2020. Like
Okay.
from the summer of 2020 on, it has sort of by permission you can go in. And that's why the COVID test went on for both grad students and faculty every 2 or 3 months since that time.
Okay.
So
I think you are in your third wave is also over, I think, in the US.
yeah, yes. Now I think it's bad in state of Michigan
Okay.
and two other states. I mean, 2-3 weeks ago it was like 20%
Oh,
positive COVID results in Michigan,
sure.
and 2 other states may have been, I don't remember which
Oh.
ones. California was getting worse too, but it got better.
Okay.
So that I really don't know. But the way I look at it, I think, things are going to change. People are not going to travel as much, more likely, even over the next 2 or 3 years, even if this gets better.
Oh.
People were traveling too much.
Yeah, that's what. And many people in our country, they are not you. Some of them, even though they have forced to put the mask, but they are not taking the mask and wearing it on the face.
I
So
see.
that's a big problem. They are not listening properly.
There's, I don't know. I hope this goes away because I think, this is one of these cases where everybody in the world has to be safe. Otherwise, any travel would cause problems in some other part. And it could very well be that the nations that could produce vaccine will become more resilient, and in some sense, one could go even further and state that the wealth of the nation may be determined by its capability of producing vaccines and medicines and all that kind of stuff, as opposed to having, regular old-fashioned wealth.
Yeah. So now now.
I should go into present now thing, right?
Yeah, you can present. You start sharing the screen, then we'll introduce, and then we'll start another couple of minutes.
Can you see my screen?
Oh yeah. We can see.
Okay,
Excuse
great.
me, sir.
Yes.
Sir, I need to welcome all the guests and including you. I need just 5 minutes.
Okay.
Shall I
We'll
proceed?
start. We'll start at 5. Another 5 minutes. Okay.
Okay, so I'll stop sharing then.
Okay. Now let it be there. We'll.
Well, let me leave the screen because I'm not that good at these things.
Yeah, because many are joining now, sir. Sir, please join, sir.
Yeah, we have some materials going up.
Okay, sir. At what time will be join, sir? At what time?
No, they will not be over.
Okay, sir. Okay.
Okay.
Welcome, Professor Vishnupal. Good evening.
Hi, Niloy. Good evening
Yes,
from
hello,
here.
Krishna. How are you?
Okay, so far so good, but you never know.
Well, we're all in the same situation.
Yeah. I live inside the campus, so we have very little population. All students have gone. All dorms are empty. There are very few faculty inside the campus.
Oh. Yeah, as you probably know, I live in this woodsy town. Not too many people live here.
Yeah.
All we have to do, I mean, we need to wear masks when we go inside the stores. But other than that, generally walking, people don't wear masks.
Yeah. That's the minimum thing one should do.
Rachana?
Sir?
Yeah, now I think, shall we start?
Yes, sir, we can.
Yeah.
Shall I do, sir?
Yeah, 1 second. I'll just give one. So I welcome all the participants, and also I welcome today's speaker, Professor NILOY Dutt, and also many of my friends and colleagues and my dear research scholars all over India and few from abroad also. So it is great opportunity to listen to NILOY Dutt. And also I would welcome Professor Vishnupal. He is a pioneer in the field of optics. So Professor Vishnupal ji, namaskar.
Thank you. Namaskar.
Okay.
Thank
So
you.
then I would like to, someone, I think, Rachana, you will be introducing the today's speaker.
Yes, sir.
Yeah, now Rachana will be introducing. Soon after introduction, Professor NILOY will take over. Okay. Thank you.
Okay, sir. Good evening, everyone. I'm Rachana HD from MCE IEEE Student Branch, Hassan. Today, I welcome everyone for the session on mode lock optical fiber laser by Professor NILOY K. Dutta. Today, I'm going to give a brief introduction about the speaker. NILOY K. Dutta received an MS and PhD in physics from Cornell University in 1976 and in 1978 respectively. He received his BSc Honours and MSc in Physics from Stephens College, New Delhi 1972 and 1974 respectively. Since 1997, he has been the Professor of Physics in the University of Connecticut prior from 1990 to 1997. He was head of the Optoelectronic Device Research Department at Bell Laboratories at Murray Hill, NJ. He joined Bell Laboratories in 1979, where he has made numerous contributions in the field of semiconductor lasers and light wave transmission system. He has published over 400 papers, 20 review chapters, and 7 patents on the semiconductor laser, optical amplifiers, coherent transmission system, optoelectronic integration devices, physics, and lightweight telecommunication system experiments. He is fellow of Institute of Electrical Engineers and Optical Society of America, the International Society of Optical Engineers, and the Connecticut Academy of Science and Engineering. He has received his Leo's Distinguished Lecture Award in the year 1995. Thank you.
Okay, thank you very much, Archana, for the introduction. Looks like a lot of stuff, but it's really, I worked with a lot of people who were pretty good. And most of them were better than me and helped me do stuff. And as you probably know, when you become a professor or a researcher, you continue to do the same kind of thing. So it looks a lot. But thank you very much for the introduction. And thank you very much for the invitation, Professor Srikanth. So I will get started. Please feel free to ask questions as I go on. And I will try to answer them as best as I can. I can tell you at this time, I'm looking out of the window and there's grass, green grass here, and looks a little cloudy, but sun is going to come out soon. So it looks pretty nice, sort of like you're looking out from outside of your office in the university where it's nice grassy lawn. That's about the way it looks here now. Okay, so I'll get started. Mode-locked fiber lasers. So I'm going to talk about primarily the work myself with my students did at the University of Connecticut. I also did some work on semiconductor mode-locked lasers. I will describe that as well so that you can sort of ask me sort of nominal questions about those. So let's go to the next slide. There's some introduction as to why these things may be needed. Then I'm going to talk about short pulse generation techniques and mode-locked semiconductor lasers and mode-locked fiber lasers. As you probably know, Professor Paul and others at the Delhi IIT, when they were there, they did a lot of work on fibers, optical fibers of various types, and that work is very well recognized throughout the world. So let's get an introduction. My work has always been associated with optical communications, not because of anything else, but simply because that's how I got started at Bell Laboratories. And as most of you may know, particularly if you are doing research in a certain area, it's much easier to continue in that area, particularly for an experimental person, because you need a lot of hardware to do the work. And you already have the hard work for the previous type of research, so you continue. So that's why all my work, even while about half of my career I've spent at the university, has been basically aligned along optical fiber optics communications. So I'm going to talk a little bit about that in the introduction. Some of you are quite aware of it, some of you may not be. So that's the next slide. This is just a tutorial on how data rates are built up. One voice circuit is 64 kilobit per second. That is when the digitized our voice. Okay, it is a 64 kilobit per second data. Now, how does 64 kilobit came about? It comes about because by sampling theorem, which basically said that you need twice the amount in bit rate if you want to transmit in an analog form up to a certain frequency. For example, if we want to go transmit up to 4 kilohertz of our voice signals, let's say 200 hertz to 4 kilohertz, we will need 4 times 2 or 8 kilobit per second data. But the voice associated with it has also had several intensity levels. That intensity will be another 8 bits, the value of that intensity. That's how the 64 kilobit per second comes about. That is, in some sense, more or less the standard for twisted pairs. Nowadays, as you might know, if you try to copy an analog signal to a digital signal, particularly voice, they will tell you, they will request if you want it copied at 64 kilobit per second or 256 kilobit per second or higher. You will see that option if you try to copy generally from a CD, audio CD, to your USB. You will see that option. I wasn't aware of it till I saw that option a few years back, few meaning 2 or 3 years ago. So what I'm really saying is 64 kilobit per second, although it is pretty much a standard, has been around for quite some time, but there are other options available now. That's how the 64 kilobit per second. So in other words, 20 kilohertz signals, voice signals, are not well represented by 64 kilobit per second. And then you have 24 voice circuits. typically it goes and it builds up into the framing bits, turns up to about 1.454 megabit per second, which is called the T1 rate. 4 T1 rates become 96 voice circuits, 7 T2 rates. There is 7 of these 96 with 6 seconds. In North America and Japan, the base T1 rate is 1.54. Europe is 2 megabit. India is 2 megabit per second. That comes about because they use 32 times 64 plus overhead. That is, instead of having 24 voice circuits, they use 32. The higher data rates obtained by SONET standard hierarchy, basic rate for SONET is 51 megabit per second, which is pretty much the same everywhere. And this built up to higher data rates 155, 622, 4 times multiplexed by multiplexing, 2.4, 10 gigabit, 40 gigabit per second. That's how it goes on. Now, of course, as you know, there is the issue of cell phones we always use. The normal cell phones works at around 2 to 2.4 gigahertz range. That's your generation 4th, generation 5th, G5 stuff operates at 30 gigahertz. That's the carrier frequency. 30 gigahertz doesn't travel too far. That is, it doesn't go through the windows and walls and so forth that easily, and it doesn't travel to the air that far. That's why you need lots of poles for G5 transmission, generation 5th. And they're generally in a big city like Delhi or New York. There are so many people, G5 is probably a good thing to do. But if you're out in the country, as most of the United States is and most of rural India is, G5 is not good because what's the point putting up so many poles? G4 is probably good enough. And then these things are multiplexed onto that carrier to get what we do these days. So now this is multiplexing concept. Let's say if you 1 megabit per second data you have, each time slot there's going to be 1 microsecond. So it's 0, 1. This is all easy stuff. 0, 1, 0. This is sort of a data pattern. Now you take 4 such data streams and compress each of these ones to small values, okay? And add them all together in time. You end up with the bottom sequence. So there'll be 32 bits now in 8 microseconds long, and there'll be multiplex data. This is the general concept of multiplexing. The reverse is demultiplexing. Okay, so when I said earlier that voice circuits are multiplex up, this is the way they do it, and they have to separate it out. And then they have to add data of various types to it. So it's a complex process, but it's done by a simple chip these days. There are several kinds. Okay, one is called non-returned 0 or OOK, on-off keying. That is simply once is a 1, 0 is a 0. So you multiplex all of them. This is the example, the top figure. The bottom figure is called the RZ, OOK, on-off keying. RZ means the ones doesn't occupy the entire time slot. Rather, it occupies a small fraction of that time slot. Okay? The reason why I'm talking about this is really for RZ transmission, mode lock lasers are important. Because mode lock lasers happen to have short pulses. They will fill within the one data stream, and they return to 0 of the signal, of the intensity happens before the time slot is up. For example, if the time slot is, let's say, 1 nanosecond, in RZ signal, each pulses would be 1 nanosecond. But in an RZ signal, each pulses could be 100 picosecond. There are advantages to doing it. That's why people, particularly as you go to higher and higher data rate, RZ becomes very important. Then there's the phase shift keying, which basically intensity remains the same, but the phase is changed. This is important for reducing things like pattern dependence, nonlinear effects, and so forth. Then Then there's a PSK, phase shift keying. For the intensity, it can happen in this form. And for the phase shift keying, for the electric field, what's happening is changing pi. Pi means, 0 pi means the intensity, there's no phase associated with it. So it looks the same. But for the electric field, it changes direction. That's what is meant by pi phase shift. So these are the types of various signals that are used for today's communications and multiplexing systems there. So this is just an introduction. Now, you might want to note how does the RZ is generated. This is a schematic of how it's generated. I'm not going to go into details, just to let you know that things can get quite complicated in a hurry. Okay. Normally, you take a distributed feedback laser, which is noted at DFV or some other type of lasers, modulate the current between two states, 1 and 0, and you get a modulated light output. But then you have to convert, make it smaller. If you want to make the time slots to be smaller, you use all this kind of stuff. You introduce it, input data, you use it. First of all, you have to use a CW DFB. Then this external MZ stands for Mach Zehnder modulator, introduces data. Then it goes to what's called a pulse carver, that it makes the pulse smaller. It takes let's assume this produces NRZ of 100 picoseconds each. Okay? The pulse carver will convert the 100 picoseconds into a 20 picosecond signal. It will take the middle 20 picosecond, leave the rest of it out. So this is another modulator appropriately adjusted in a certain way. This is the bottom figure, shows you much more complicated design. It's called differential quadrature phase shift keying system. Quadrature phase shift keying means, quadrature means pi, 0 pi. Instead of that, it will be 0 pi over 2 pi, 3 pi over 2, 2 pi. So in other words, 4 phases within one cycle. That's a quadrature phase shift keying. This is a differential quadrature because the differential enables you to do certain things which the regular one doesn't. My purpose of showing you these two pictures simply to state things can get quite complicated very easily, both in the experiment in the lab and even in terms of analysis, because every one of the elements would introduce lots of jitters. So the best thing to do is sort of normal on-off things. People have worked on these things for quite some time, but it's been very difficult to put into practice. Unlike in wireless transmission, where phase shift keying is the normal thing to do. As some of you are familiar with wireless transmission who knows that 4 sets of frequencies, 4 sets of phases, and 4 sets of amplitude levels are quite common. That's called 16 QAM. Modulator signals. So, whereas here it gets to be in optics, it gets to be quite difficult to implement. It has a lot to do with the receiver sensitivities, phase sensitivities, and so forth. I won't go into details, but all I wanted to tell you, they get very difficult. And many times when I work with these things, I work with other people, meaning people who are not at the university, but rather with companies. My work at the universities is aimed at smaller things like generating mode-locked pulses, which is a much simpler operation. Just to tell you what today's optical communication looks like, it's no longer the case of X number of strands of fiber going across the Atlantic or the Pacific or along the coast or in the terrestrial lines. Optical transmission is used in data centers, meaning these data centers are essentially banks of computers which store data, transfer data from one place to another, and so forth. So there are lots and lots of fibers that are involved. And they work at fairly high rates of each fiber can easily carry 10 gigabit per second signals. Certainly 2.4 is quite common, and they're bundled up to get almost 10 terabits of signal in data centers. So that's why we can get what we can get so easily using the clouds servers, which are connected to the data centers and so forth. They're all basically banks of computers which can interconnect to each other. And we can access all the information stored anywhere using simply typing something in Google. This is an amazing thing if you really think about it. And I do believe, this is my opinion, not anybody else's, that if things like COVID continue to happen, it happened once, people have to communicate through these data centers and so forth all over the world, like we're doing this particular meeting. Okay, let's go to the next slide. Well, now I'm going to show slides of my lab. These are the pictures I took yesterday morning. I went over there and took pictures. So this is essentially shows you an optical table. I have a bunch of slides. Okay, this looks like this is an optical table. It's a bunch of fiber. This is where the fiber lasers are. This is to control all the various electrical lasers and such on top. This is power cables, power hangs from the roof. This is an optical amplifier. I have about 1, 2, 3, 4, 1, 2, 3, 4, 5. I have about 7 optical tables like this in my lab, and they're all full of stuff. This is probably the heart of the instrumentation, this rack. Essentially the top instrument here. I hope you can see the cursor. The top thing here.
Yeah, cursor is moving.
Okay, great. Thank you. The top thing here is an optical spectrum analyzer. The second item here is what's called a synthesizer, which is a signal generator, sine wave generator, but the word synthesizer in this case implies that its frequencies are built up from a very stable crystal oscillator. These things cost a little more. So as a result, it's possible to tune the frequency at an extremely good accuracy, 1 megahertz. You can tune 10 gigahertz, which is about 10 to the 4 times 1 megahertz to an accuracy of 1 megahertz, or even less. See, that's what this is the heart of our system. Without that, we couldn't make fiber lasers work. The third one is an oscilloscope, which has a bandwidth of about 40 gigahertz or so we cannot see very well 100 gigahertz signal, but I'll show you some pictures. The third here is a 65 gigahertz RF spectrum analyzer. This is the top one is the optical spectrum analyzer. This is a signal generator, oscilloscope, RF spectrum analyzer. This is a low speed bit error rate generator, which is I think it's about 10 gigabits or something. So we have a bunch of stuff here. The stuff here that you can see is a homemade high power optical amplifiers. High power, this was made about, I would say by now, 20 years ago. This produced about 10 watts of power. These little things which you cannot see probably are basically pump lasers that are connected together. This is all homemade. There's nothing here that's outside. There's a bunch of things. So, and here I have this, the light blue box is these two boxes are really autocorrelators. They are capable of measuring pulses to less than 100 femtoseconds width. And the stuff here is simply another scope, low speed scope. We have it all configured so that we, meaning the student, as it all configured so the data can be displayed on the computer, the standard PC kind of thing. And the output to both of these things, input to both of these things will be an optical fiber input. So the alignment is not really necessary. I mean, the old-fashioned alignment. So these are simply bit error tests. These are old ones. I think these are like 2 gigabit bit error testers and so forth. These things, top 2. And the bottom one, I think, is a 5 gigabit bit error testers. This is a bunch of, these are 2 optical amplifiers that we bought. These are the high power amplifier, meaning they produce about 1 watt. They were much easier to do it that way. You can send them out and they repair it. The biggest problem with these things is when you have any kind of dirt or dust at the end of the fiber, it burns up. Okay, 1 watt is enough to burn up the end of the fiber, then nothing, no output will come out. That's the biggest problem with these things. But there's 2 of them. One is a high gain, gives about 30 dB of gain to an output power of about 10 watts. The other one is simply a 1 watt amplifier. Okay, what you see here is a few things. The coils here is typically an erbium doped fiber. This is how I get them. We splice at the ends of it, the single mode fibers. That's how I use them. This is to see things and so forth. This is another optical table. I have lots of fibers of these types just to show you. This is an bit error tester that I have.
So can we ask a doubt in between?
Sure.
First of all, my greetings and respect to you and to Vishnupal sir also. I am a student of ID Delhi batch. So I am working in ISRO and I have one question regarding EDFA. Sir,
Yeah.
Actually we also are developing EDFA till 5 watt for space grade, and we see the issue that output fiber, but you see the last third stage after MPC, multimode power combiner and NBM, that got burned every time, that junction. So it is a heat problem or something?
No, yes, it's a really heat problem. Anything more than 1 watt coming out of a single mode fiber, you really have to be careful. You have to have a nominally a dust-free room. Doesn't have to have 1,000 clean room or something, but you cannot have too much dust in that room. Because it so happens that the dust like to collect at the end of fibers whenever there is light versus no light coming out. Well, I'm probably being facetious here. That may not be correct, but dust likes to collect at the end of fibers because there may be something, it's some gel, something gets in there instead of oil. Any oil drops anywhere would cause you problems. We experienced that a lot in making these 1 watt or 3 watt amplifiers that we made in, I think in the time frame around 1999 to 2002. It had to be extremely careful, and it won't last for very long because what will happen, the end of the fiber will get destroyed. So I have to leave the fiber up, splice another one, and then it'll start working.
Start from zero again. Yes, we have to start from zero again. It burns like...
Yes, yes, absolutely. I mean, you have to be very careful with the splice too. It has to be a very low loss splice. It is a problem, anything more than 1 watt. And believe it or not, I said the same thing. We have today, no, I must say I've been fortunate enough, and Professor Paul and several other people have been fortunate enough to have worked in an area where their output is quite visible in the sense that other people are using the same thing. So we have researchers here who buy these high power fiber lasers. They don't buy argon lasers or whatever it is for their experiments anymore. They buy neodymium pump laser, terbium fiber lasers, not erbium, terbium fiber lasers, but that's at around 1 micron. They pump it with something, slightly lower.
Right.
In any case, gallium arsenide. So they have huge problems, and they don't know. They haven't built it, right? So something happens inside. They have to send it out, and comes back in 4 months, fixed. They work it for a month or 2. Again, the same problem happens. It's basically you have to operate in a dust-free room. Even simply putting an enclosure, like a plastic enclosure, plastic sheets, I don't know what you must have them there. They're about 1/4 inch thick, comes transparent or comes this orange color. Put a box around the stuff. so that, touching the table so that no dust gets in, or it's an impediment for the dust to get in. That alone would help tremendously.
Thank you.
Anything
May I
less
say-
than
may I-
2 watt, it
may
doesn't
I-
matter.
May I say something? Comment here, Niloy and Vikas. Yeah.
Yeah, thank you,
So
sir. Thank you.
You see, I'm talking of what I sort of found out while working in the lab in around mid 1970s. I was in Trondheim in Norway. I used to measure the near field technique to measure the refractive index profile of the fiber. So fiber had to be very clean. So that was the same problem. If there's a dust, the profile gets distorted because you are measuring the field itself generated from the end of the fiber. So one, I think, which I have found out to be very useful is just use a Scotch tape. Just touch it, end of the fiber, it will remove the dust. If you have an option of the bare fiber at any point in your system. So that's very, very useful actually. And almost 100% it used to work. I talked, one David Payne was visiting us and we were discussing that, and he also greatly appreciated that. Oh, that I never knew that you can do that.
Okay, so definitely.
I'm talking of mid 1970s, so it should still work.
Great, thank you. As you can see in this picture here, there's a Scotch tape up top.
Yeah. So
That's what
just
that
use
is.
that as a very simple technique to remove the dust. People talked of ultrasonic cleaning and all those stuff, but I found this is a very useful, handy technique to clean the dust from the end of the fiber.
Thank you, sir. Thank you.
Thank
Yes, sir, one more question. Anything that can help us in space grade, because we are working for space. So generally what happens, we can use this EDFA 5 watt and 10 watt to ground. They can work for 88 hours operation. But when we go to thermovac chamber, so they burn in 1 minute and the whole stuff got waste.
Okay. Now, I'm going to tell you something that's probably I'm not supposed to say, but anyway, I will tell you, it's been a long time. I used to work on 10 watt, developing 10 watt airborne amplifiers. Okay. They needed about several 10 watt gallium arsenide lasers to be pumped to produce such amplifiers. Thing that used to happen, what we found is what happens there's a coating on these lasers that has to be the lasers are air coated. I don't know what you found is the same thing or not. Let me first tell you. See, I really don't know because I'm not there. What we found is this is during the period around after I left Bell Labs. So that'll be about 1997 to 2003 timeframe. I was working on huge projects, such as defense industries and stuff like that. The gallium arsenide lasers have a coating on them. The coating absorbs oxygen. Okay. And oxygen has a tendency, carbon gets deposited on top of it. Okay, and so any carbon, if there is no oxygen present, I believe I remember it correctly, if there is no oxygen present in the atmosphere around the lasers, that carbon that gets deposited from the outgassing of the various hydrocarbons that are present in the system, glue and whatever it is, solders and stuff, because you're in vacuum, they're going to get deposited on top of it, on the facets. And that is going to create centers for absorption of the light that is coming out, and eventually it'll melt the facet. Initially, it's simply going to degrade the light output because the band gap goes down near the facet, so it increases the absorption. After that, it's going to degrade the facet enough that the laser is going to burn out completely. So we found this to be a laser burnout problem, more or less in the absence of oxygen. The oxygen, what it did is it became combined with the carbon and became CO2, and it disappeared. This seems amazing, but it did happen. And I'm not sure what you're doing it from. All I can tell you is,
So we are also facing our lasers are burning. Our pump diode lasers are get burned.
yes, if the pump lasers, so that's probably what is happening. If you look at the facets and examine them, there will probably be carbon deposits.
Yes, sir. We definitely look at, sir. Thank you, sir.
So, but I don't know. I don't know what is happening in your case, and I can tell you a lot more about it, but this was, I'm probably not supposed to, but anyway.
Okay, sir. Okay. In any other forum, we can discuss. Okay.
Yeah, yeah.
Thank you, sir. Thank you.
Sure. Now, another thing, if you want, you can check this. Put it in an oxygen atmosphere, see if the laser recovers. If it is not gone that far, it might recover. There is a carbon will be oxidized by the oxygen present in the normal atmosphere, and the laser may recover. That was observed back then. Okay, so on this picture, what I have is a homemade optical amplifier. We do things by homemade. We don't buy everything. This thing here is a pump laser, 980 nanometer. There are a couple. The black spool here is the erbium doped fiber, typically 30 meters or long. These are a bunch of homemade splices. As you can tell, these are the amplifier output, two ends of the, after it goes to the amplifier. And the back here is sort of pedals. We use essentially, those are polarization controllers. If you have a fiber that is wound up in a circle, and you move that pedal, it changes the polarization of the output. And in the front here is their splicer. Okay, this splicer is quite okay because we can see what's going on. It doesn't measure the loss, but it will tell us how it looks very well and when to hit the button so that it does the splicing. It's pretty good. It's not the latest version that's available today. And the bottom part here is the cleaving fiber and the small box. This is the details of another erbium doped amplifier. Again, this is the amplifier spool. These are the two pumps. These are 980 nanometer pumps, which we purchased. They're on a temperature controlled mount. And the reason why tapes are used to tape them in place is because any vibration of the fiber will cause a change in the length of the fiber in the fiber laser setup. We don't want to, if we want a stable output, we cannot let that happen. So that's why they're kind of taped in place. And this thing here, there's what's called something that lets in light only one way. That's what these are. These are homemade splices and stuff. There's a lot of them. This is a homemade splice. This is a splice that maybe we bought, or maybe it's homemade. I don't remember. But there's a bunch of these things all over the place. There's another fiber laser. This is a fiber amplifier, probably for amplifying the output. Again, two pump lasers and a bunch of control circuits. This is the entire another setup of various types that exist in my lab. We can look at semiconductor lasers, amplifiers, and so forth in your microscopes, various types. This is an instrument that measures cable TV analog outputs. Okay? Measures analog properties, not digital properties. Bit error rates measures digital properties, analog measures analog properties. So carrier to noise ratio and mixing, all that stuff can be measured in something like this. And as you can tell, this is an old transistor curve tracer, which some of you may have used or maybe still used. I'm a 1970s person. And when I came to the university, I took everything along with me. So all that stuff came along. That was very useful for setting up. Again, this is the signal generator, temperature controller. These are all things associated with power supply for lasers. These are the pedals. So the fiber goes through, makes one loop around this. There's three black things, one loop around this, one loop around this, and comes out. So when you move these pedals, simply twist them, it introduces strain in the fiber and changes the polarization of the light coming through. So you need this polarization control in a fiber laser. This is a lithium niobate modulator. It comes by this particular form. This is the RF output, the fiber input and fiber output, as you can tell. Here is the fiber output and the fiber input, and the lithium niobate, the RF input that goes into it. It could be differential, it could be single. That's the way it's done. But the modulator sort of looks like this. This is another picture of the same thing. And I'll picture a bunch of, this is the way I have it set up. This is more or less so that they can work on this side or work on this side, either side of the table. Okay, so I'm going to go into optical short pulse generation technique. This is much simpler than what I first stated in the deep, this differential quadrature phase shift keying techniques. I mean, before you go that far, you have to generate short optical pulses. This is sort of the history of how we worked here in the university. First, we use cascaded lithium niobate modulators. I will show you how it's done. Then we worked on mode lock semiconductor lasers. I'll tell you what they're. Then we work short pulse generation using fiber nonlinearity. Then I'm going to discuss mainly mode locked fiber lasers. In a lithium niobate modulators, you could set up based on the apparatus that you saw. You can simply set up such a thing. You take a distributed feedback laser, JCW, run through a polarization controller, because this is M1 is a Mach-Zehnder modulator. Lithium niobate Mach-Zehnder modulator. It likes the polarization in a certain way. Okay? So it's got to be linearly polarized light. That's the purpose of this. Fiber will tend to rotate the polarization somewhat. That's why we need this polarization controller. This is a second polarization controller, PC2, in front of the second Mach-Zehnder modulator. They are driven by the same signal generator so that they're in phase. There's a phase shifter here to change the phase in a deterministic form. Then it's amplified and goes through optical spectrum analyzer. I don't know what it is, autocorrelators, electrical spectrum analyzer, scope, etc. So this is 20 gigahertz pulses generated by this, such a thing, and 40 gigahertz pulses. The reason why they don't look so good, looks in this particular form, this was done well ahead, and my students at that time, this is probably from about 2002. We're not that familiar. We didn't have the latest of the stuff. So in any case, that's the way it looked. This may be scope traces also. Now I'm going to talk about mode locking. Some of you may know what mode locking is. Mode locking is the technique used to generate short pulses from a laser. It turns out the mode locking was invented at the University of Connecticut by somebody named Tony DiMaria when he worked for the United Technologies Research Center. Basically, in this technique, the phases, a laser typically lays in many longitudinal modes of the cavity. If somehow you lock the phases of the longitudinal modes, that is, all the modes are in the same phase, then when the gain or loss of the laser is modulated at the inverse round trip time of the optical cavity, you'll get a short pulse. This can be shown very easily by summing up the electric fields of a large number of modes, and this will be just like a grating. Some of you have probably done, how does the grating output comes about? Meaning orders, 0th order will have a lot of light, and the first order, second order, etc. You sum up the individual fields from each of the several sources in the gradient. Sources meaning each of the lines of the gradient. They've diffracted someone, they reflected each of those lines, light from each of those lines, they interfere constructively and produce this 0th order, first order, second order mode. And the larger the number of lines, the sharper is the grating lines at the output. Okay? It's very similar in principle of mode locking. That's how it ends up with a short pulse from a laser. It naturally generates short pulses when the laser is modulated at the inverse of the round trip time of the optical cavity. That's the principle of mode locking. I could have had a bunch of equations, each you can find in typical book and look it up. You'll find that's the case. A typical mode locked semiconductor laser, so this look like in this particular form. This is the laser, which will have a DC bias associated with it, and sort of something modulated at the round trip time of the cavity. Or you can move the mirror. The pulse repetition rate will be C over 2L, where L is the total length of the optical cavity, and C is the speed of light. Now, from this simple description in the previous slide to this, it becomes somewhat difficult when you try to make a colliding pulse mode locked laser. Let's not worry about colliding pulse at this stage. When you want to make a mode locked laser, it's good to have a saturable absorber. Saturable, that's what SA means. Saturable absorber is something which absorption becomes less if the intensity increases. Okay? If the intensity of the light increases, then the absorption becomes less or saturates. So this is the colliding pulse mode locked laser that we worked on. This is the laser cavity. The whole thing is 8.6 millimeter because we wanted to make something that operates at around 10 gigahertz pulses. These are the RF contacts you have to have at both sides. And then you have the amplifier in this case means simply gain region. Amp means gain region. This is a saturable absorber in the middle. Basically, it's the same active region, which is separated out with a slightly lower current to produce a saturable absorber. You probably know a semiconductor material, if you put enough current into it, will have gain and be made to operate as a laser, therefore. If the current is less than that amount, it's an absorber. If the current within a certain range, it can act as a saturable absorber, meaning the absorption will go down if you increase the intensity. In this particular case, for this 8.6 millimeter, that's fairly large for a typical laser. Typical laser is about 1/4 of a millimeter long. Okay? Travel time between the two facets, 100 picoseconds, round trip time is 200 picoseconds. So pulse repetition rate, because it's what's called a colliding pulse, meaning pulses are colliding in the middle and are saturating it. So the pulse repetition rate in this case is the C over L, which is 10 gigahertz. You can ask me about it. I can explain why that is the case, but for the time being, you can believe me that that's the way it works. It's not C over 2L for a colliding pulse mode locked laser, rather it's C over L. So it's about 10 gigahertz. The disadvantage of this mode locked laser is that the frequency of operation, as I said, for telecom system is very precise. It cannot be about 10 gigahertz. It has to be precisely 10.01, whatever it is they need, gigahertz. And that's very difficult to do here because it's determined by the cavity. That's one of the disadvantages of the semiconductor mode locked lasers. Although they are very stable, even for laboratory experiments, they're very difficult. Because unless you change the experiment so that it doesn't match whatever frequency you want, it's very difficult. But in any case, this is the optical pulse generation scheme. It's basically the pulses from both ends come and meet here and saturates the absorber. That's why the pulse repetition rate is the way it is. I won't go into details. Pulse widths of about 1 picosecond can be obtained. This shows pulse width as a function of frequency. As I said, this one happened to be at 9.6 gigahertz in this particular range, 9.5 to 9.7. It produces pulses. And shortest pulse around 9.6 gigahertz. These things will depend on the bias voltage of the saturated absorber and so forth. Here is another colliding pulse mode lock laser. This is simply made much shorter. So now you have to print all these things on the semiconductor material. Print meaning print the lines for various gold lines on it. And you get about 350 femtoseconds or 0.35 picosecond pulses generated. And the frequency is about 300 gigahertz. So this is a very fast one. Yeah? The length of the laser is quite small. It's I think 250 or 300 micron. Length meaning from this end to that end is quite small. In the previous case, it was 8.5 millimeter. Here it is 0.35 millimeters. Okay. Simplest way to generate short pulses is using fiber nonlinearity. This is what I'm talking about in this slide. You take a distributed feedback lasers, of which we have plenty, or you can easily buy them these days. Run it to 600 meters of dispersion compensating fiber. Run through various types of fibers. One can simulate these things reasonably well. And then run it through a bandpass filter. So reduce the spectral width. Then 2 kilometers DSF, dispersion shifted fibers, and 300 meters of standard single mode fiber. Increase the pulse width, run through 30 meters of single mode fiber. And this basically rate doubler, 20 meters, and this is what this circular thing does. This is basically an isolator. It basically lets it go only one way, because so there is no reflection into the back into the system. So you can get all of these things. I mean, the reason why these numbers are written here, 2 kilometers, 600 meters, because we modeled it using a standard, it's called nonlinear Schrodinger equation for the propagation of pulses through a fiber. And these turned out to be about the right number to use for the particular type of lasers we had, because we knew the value of the dispersion for all of these types of fibers. And I have all of these types of fibers and put them together to get this. And we were able to get, the advantage here is that you can tune the pulse a little bit, that is vary the frequency of the pulse a little bit. Here's an experiment result, compressed pulse width. Okay, compressed means this is the pulse compressor. It sort of doubles it somehow, okay? And of course, this is compressing the pulses to all of it. This is the experiment, this is a simulation. And so you can get relatively short pulses with it. This is, after first stage compression, you can get pulses of the order of 200 femtoseconds, as you can tell this for this fiber length. You have to optimize the fiber length to get the shortest pulse. As you can tell, this is the last length of the fiber. In other words, we are talking about this thing here that's written as 30 meters SSF. This compresses also. This is a standard single mode fiber. So tunable 180, this is a autocorrelation trace of the 180 femtosecond pulse. We can get these things. Okay. Now, this is basically different types of pulse width and time bandwidth products. And so these are pretty good in the sense of after the nonlinear loop mirrors and so forth. Okay, let's go back. Let's go to the original intent of this topic, this thing, which is mode locked fiber laser. This is a typical mode locked fiber laser. Okay? All parts that we use are commercially available. In my case, some of the parts were homemade, like erbium doped amplifier, but you can buy them too. You can buy an isolator that's typically looks like a cylinder, tiny cylinder with fibers coming out. You can buy these tunable field, you can buy couplers. Polarization controllers, you can buy them or you can use pedals. We use these handmade pedals. This is the lithium niobate modulator that we can buy. This is the synthesizer. This is probably the most expensive part of the whole apparatus. This is an amplifier because you need few watts of power. And the synthesizer doesn't produce that much power. There's another isolator. This is the pump laser for the erbium doped fibers. So all of these things, the reason why we studied mode locked fiber lasers was for doing high-speed optical communication experiments and high-speed optical logic experiments. Optical logic meaning Boolean logic, XOR, OR, and sort of higher functions of those things, such as pseudorandom word generators and so forth, which I am not going to discuss. I'm just going to discuss mode locked fiber lasers. For this particular laser, typically the length, total length is about 60 meters. 23 is in the fiber. There's a bunch of other things here and there. So cavity round trip frequency, that is by how long it takes for a pulse to go around the system, is C, which is speed of light, divided by L. It's going to be speed of light in the fiber. So that's going to be about 3 to 5 megahertz. I think I made a mistake here, it looks like. It should be about 3 megahertz because speed of light is reduced by 1.5 in the fiber. Okay. So should be about 3 megahertz for going around the system. Now, this is kind of important. Now, the synthesizer becomes important here because synthesizers will have to now produce a frequency in multiples of 3 megahertz to an accuracy of 10% of the value of 3 megahertz. Okay, that's what normal signal generators will not do that. So you need that's how HP calls it. HP means Hewlett Packard Company, called it synthesizer. That's what we bought. Normal signal generators will not allow you to get the frequency that well adjusted. But the purpose of the reason why we went to fiber lasers, everything was in our control. We can buy the parts from various people, put it all together, and the results that we get are going to be competitive depending on how well we put it together, how capable we are in thinking about new stuff. Was not dependent on other people giving me semiconductor parts or something. In the colliding pulse mode lock laser case, I had to work with Bell Labs to get them to make this thing and so forth. Now, as the organization changed, I couldn't get those things. So I had to get back to doing something different. And that's how I ended up working with fiber lasers. And I find it to be very, very easy, particularly for lab work and certainly for applications like, airborne fiber amplifiers, communications in space and so forth. These things, it's good to have expertise in several of my students got hired in defense contractors here because they had expertise in fiber splicing, working with fiber, knowledge about different types of fibers and semiconductor lasers and so forth. So that was kind of important for them. Okay, there's something called harmonic and rational harmonic mode locking. That is the modulation frequency that you put in. In the past, I said the modulation frequency must equal the round trip cavity, inverse of the cavity round trip time. Okay? It turns out it doesn't have to be that. It could be any harmonic of that. That is, if the modulation frequency, this modulation frequency meaning the lithium niobate modulator that I put in the fiber laser case, or in an external cavity big lasers, you can modulate with something else such as acoustic waves. That modulation frequency does not have to equal the cavity round trip time, inverse of the cavity round trip time. Rather, it can be an integer multiple of it. Okay? If the modulator, then the pulse repetition rate will be very high, will be the modulation frequency. That is, if I were to make 10 gigahertz pulses, I modulate the lithium niobate modulator at 10 gigahertz. And the cavity round trip frequency, if it is 5 megahertz, the N becomes 2000. So we are modulating at 2000 times the cavity round trip, inverse of the cavity round trip time. Even then, harmonic mode locking will take place. Then there was something called rational harmonic mode, which fortunately we were able to demonstrate first. We just happened to be there. It's pretty much surreptitious or serendipity. If this modulation frequency equals the N, which is the integer, plus 1 over P, which is P is an integer. P could be 2, 3, 4, 5. The pulse repetition rate becomes P times FM. So let's say FM is 10 gigahertz and P equals 4. Then it will get 40 gigahertz pulses out of it. It's much easier, therefore, to generate higher and higher speed pulses. You can use the same setup, the change your frequency. The only thing you have to be able to sort of do this. That is, you need the synthesizers. That is, fractions of the cavity, inverse of the cavity round trip time. Your synthesizer must be able to produce those frequencies, stable frequencies at that rate. Only then this will work. So here is the pulses at 100 gigahertz by 10th order rational harmonic mode locking. This is the picture from the scope, which doesn't have high enough resolution, as I told you, its resolution is about 40 gigahertz bandwidth. So it's all mixed up. You don't see, it looks like it's like an on-off going on. The pulses, these were about 3 picosecond wide pulses, 100 gigahertz. We've also generated 1 picosecond pulses. This is an example of a 1 picosecond pulse. All of this stuff works around 15, 55 nanometers or so, because that's where the erbium doped amplifiers work. That's where my lasers are. Most of the systems that I have in the lab works around 1555 nanometers. Again, that's probably because my background is in optical communication. That's where the communication systems worked best. These days, many people use terbium fiber lasers, primarily because the terbium fiber lasers produces much higher power than the erbium doped fiber lasers, or even the erbium and terbium fiber lasers. Fiber lasers are used these days for many high power applications. In those cases, the terbium is the medium of choice. This is the 40 gigabit pulse train. This shows the autocorrelation train of the pulses. Again, in this case, the value P that I said, N plus 1 over P was 4. So the lithium niobate modulator is driven at a very precise frequency. So you get this nice pulses. They're about 1 picosecond wide. This is the optical spectrum. Mode locked pulses will have a wide optical spectrum, because as the pulse narrows, the spectrum becomes larger. We were able to stabilize these fibers using a feedback circuit. This feedback circuit is very similar to what is used in electronics. It generally uses a voltage controlled oscillator. It's called the VCO. which actually drives the Mach-Zehnder modulator. The frequency of the VCO, the voltage controlled oscillator, is stabilized using this feedback circuit. Okay? This is pretty much what's called a phase locked loop in electronics. And this loop is gets locked to a certain frequency. And that's what is driving the Mach-Zehnder modulator. And as a result, the fiber laser frequency also gets locked to a certain frequency. This is the easiest way to make the fiber laser operate at a very precise frequency. Because as I said before, this thing is spread out over the table. So he's affected by the vibrations. Any small change in path length will show up at a change in frequency, vibrations, temperatures, and so forth. We don't want any of these things to happen. Just by enclosing this, putting a piece of plexiglass over the whole thing helps significantly relative to these effects. But the feedback circuits, of course, is an active stabilization, and it can do it quite well. There's a bunch of things here. I won't go into all the details. SSM stands for single sideband modulator. This is an offset frequency that gets multiplied, and the difference between the two is minimized and transferred to the voltage controlled oscillator, which generates the output, and the whole thing is stable. This is a typical, if some of you are familiar with the phase locked loop, that's how it's done in electronics. We can also double the repetition rate. You take this output of the mode-locked fiber lasers, basically one path goes straight down or goes through here, goes straight down. The other one gets shifted by half the time difference between the two when it travels through this loop and comes out and separated in between. That's how 80 gigahertz becomes converted into output of 80, from 40 gigahertz gets converted into 80 gigahertz. This is the autocorrelation trace of the 80 gigahertz pulses. So it's possible to double the repetition rate. This is an 8th order rational harmonic mode-locked pulse train. That is, P had a value of 8, and this is operating at 80 gigahertz, not gigabit per second. This is the modulator transmission intensity, oscilloscope trace. This is the optical spectrum of the pulse. It's quite broad, as you can tell, from 1555 to 1559. And this is the autocorrelation trace, or the pulse train. So it's possible to do all of these things. See, fiber lasers allows us to do all of these fooling around, which with the semiconductor lasers, you got to go through the growth, fabrication, all of that stuff, which I don't have a capability of. When I came from Bell Labs, I was doing all of that stuff at Bell, but when I came here, I figured the students are not going to be interested in doing all that stuff. Also, it's going to be very hard for me. So I decided to focus on basically measurement and characterization, analysis, understanding of the measurements, not on growth and materials processing. For that, I go to other places, including Sandia Labs, Bell Labs, Boeing's, etc. So fiber lasers became quite an easy avenue for me to get short pulses. This is just an experiment. It's a dual wavelength. You can get two wavelengths simultaneously out of it, provided this is the modulation frequency of 1. I mean, if you think about it and go back, you'll find this to be the formula for the modulation frequency that is needed, because this is the cavity, inverse of the cavity round trip time for one wavelength. This is the inverse of the cavity round trip time for the second wavelength, because L2 and L1 are two slightly different lengths, because one travels along this path, second one travels along this path. This multiplexer means 1 to 2 coupler here. Demux is 2 to 1 back. It uses essentially the same thing. You can get both of them to work only if the modulation frequencies for the both are the same, because they're using the same modulator, and it's possible to get two different rational harmonic mode-locked wavelengths out of it. These are the two different wavelengths, one at around 1545, the other at 1557. This is the RF spectrum. This is the optical spectrum. This is the RF spectrum. And these are the autocorrelation traces of the two wavelengths. They look pretty good. So this is it. You can probably make 3 wavelengths laser too, but you have to work a little harder. The multiplexers will be 1 to 3, and the demultiplexers will be 3 to 1 and stuff, so forth. And then it's possible to do that. Now, it's possible to make a PCF-based optical pulse compressor as well, meaning PCF means photonic crystals. Photonic crystals, as you probably know, that's at least some of you, it consists of basically hollow regions inside the single mode or a multimode fiber. They have a high nonlinearity because most of the light gets concentrated in the middle, with a much smaller region that will be in a typical single mode fiber. So as a result, intensity goes up by a factor of 10. So seeing from the outside, nonlinearity goes up from the input intensity point of view. Okay, that's a simple enough explanation for the high nonlinearity. It's because the high confinement of the light. So this is the dispersion parameters. This is how they look. Some of you may have seen pictures. So what we did, we used a nonlinear loop consisting of photonic crystal fibers to get shorter pulses. Basically, the pulse of light comes in, goes through this nonlinear mirror, but polarization controller is always needed in these things. What comes out is a shorter pulse. Because of the destructive interference that takes place here. Again, these will take a little bit of time to understand and the details involved in it, but it's possible to do. It's not that difficult. I'm just showing it because this is the nonlinear Schrodinger equation from a book by Professor Agarwal. It's titled Nonlinear Fiber Optics. And U is this quantity. A is the amplitude of the pulse. The dispersion parameters involved. You can solve this equation because there is no feedback, so it's possible to solve it using Mathematica and get the results for all the modeling that we were talking about. I won't go into details. You know, you can use, they used split step Fourier method to solve this. These are my students that made this thing up. So what it's essential, this is the result. Optical pulse width does indeed go down. If you use one nonlinear loop mirror, second it goes down further, third goes down further, fourth goes down even more. And again, for input pulse energy, it looks like this. With input pulse width, the effect is in this form. In any case, the more the number of nonlinear loop mirrors, the more the pulse goes down. So the cascaded, if you use 2, it'll give better compression results than a single. Okay? And the performance is better if the input pulse width is sufficiently low. That's all we get out of the modeling. It's very important though. The fact that it's continuously decreases the pulse width is an important thing because we can get shorter pulses using this method. So here is an experimental setup, again done with all the stuff that I have in the lab. So this is the fiber laser. It can be made to operate either at 20 gigahertz or 40 gigahertz. Erbium doped fiber amplifier going through another, this is another pulse compressor to get the pulses to 2 picoseconds. Remember, less than 2 picoseconds gives you better results. And then this is a nonlinear loop mirror, which this is it's a PCA-based compression in the ring structure. Why ring structure? Because then we can use the same mirror twice. It goes through the same loop twice. That's how it became a ring structure, to realize cascaded compression. Okay. So there's a bunch of stuff, pretty much all the stuff that I showed you is needed. This, and then this is the pulse train. This is a 20 gigahertz pulse train. This is the 40 gigahertz pulse train. That is 40 gigahertz pulses at 570 femtoseconds is the pulse width here. This is a 20 gigahertz, 610 picosecond. Please don't ask me why is it 600 versus 570. I have no idea. This is what they found. And the average power is 3 to 5 milliwatts, and peak power is about half an watt. So it's possible to get about 500 femtosecond pulses at 40 gigahertz using these techniques. Now, another way of getting these pulses would be used, mode lock pulses would be using a saturable absorber. We have used saturable absorber like a carbon nanotube, which calls here, or a graphene. We've used both types. This is what saturable absorption means. The absorption percent is about 60%, and it goes down to 10% if the pump power exceeds about half a milliwatt. That's what saturable absorption means. Okay. If you use saturable absorption, as some of you may know, in an optical laser cavity, it can produce pulses. In principle, it can produce mode lock pulses at the inverse round trip time of the cavity. So these pulses that are produced here are at about 360 femtoseconds, but it is a pretty low repetition rate of few megahertz. But the pulses are quite short. Okay. So far, I've been talking about erbium doped mode locked fiber lasers because that's what I had a lot of. But people have made ytterbium doped fibers. Ytterbium doped fibers are actually more useful, making very high power. Ytterbium, you can put a lot more ytterbium in a fiber without having what's called the conversion scheme. As a result, it can have much higher gain. And also, as a result, its saturation powers are high, so you can have very high power fiber lasers out of ytterbium. So you can make mode lock fiber lasers in the same way out of ytterbium, using ytterbium doped fiber, as in the case of the erbium doped fiber. But it's possible to amplify them to much higher power levels. People have generated hundreds of kilowatts from ytterbium doped fibers. And the fibers have the additional property that they can amplify very high peak powers, because the lifetime of the states are very long. Okay. Now, if you want to ask me why is ytterbium doped fiber produce higher power than erbium doped fiber, I'll give you the standard answer, which you cannot dope a fiber with erbium to as high a level as with ytterbium because they precipitate, they cause problems, and there is a phenomenon called conversion that takes place. That is, ytterbium cannot produce that high again. Beyond that, I don't know how it relates to the atomic structure. I can probably come up with some hokey answer if asked, but I really don't. In other words, a lot of these things as to which dopant works better, which rare earth dopant's better than the other ones, and in which host, it's sort of an art. People figure out, people have some rules of thumb that they know, and that's how it works. It's not an exact, it's not like the energy levels of the hydrogen atom. It's not known that well. Okay, so it pretty much looks like this. This is also a carbon nanotube. You can use carbon nanotube as graphites. Both of these are basically soot, soot-like material. Soot, the carbon that gets deposited when you burn something, is very similar material. You can put it at the end of the fiber, okay, with a Q-tip, and simply, put the two fiber ends together back again in the connector. And you might get some effect. Eventually, you get pretty good at it. Eventually, meaning a couple of days of tries, you get good at it and you get it reproducibly. You can remove it with a Scotch tape and put new ones in and so forth. And you can measure their saturation properties by measuring this absorption. Then you know a lot more. So in any case, the terbium doped fiber laser is also possible. People have made such things. These are the pulses generated. 92 picosecond pulses were generated. Then they can be compressed. Now, there are several pulse compression schemes exist. Grating-based pulse compression schemes, nonlinear loop mirror-based pulse compressions, and ring resonator pulse compression schemes. Grating-based pulse compression is by far the most widely applicable because it can be used on any kind of wavelength, because gratings can be made pretty much that operates in various wavelengths. So for a terbium doped fiber laser, it's probably better to use gratings. And here they got about 580 femtosecond pulses. Now, what do you do with this? Sometimes you need high peak powers. This that somebody mentioned is called the tapered fiber bundle, in which basically you need a double clad fiber. Double clad fiber has two claddings, a single mode cladding like this, and a larger cladding about 100 micron diameters. And this pump goes into the higher outer cladding, but it continues to produce gain for signal traveling along the center. Okay? People would not have believed it had it not worked. And as a matter of fact, the power conversion takes place in a very short length. Very short, meaning 10 centimeters to a meter can happen, this power conversion. It's entire gain process. In order to get pump light into the outer cladding, which is 100 micron diameter, inner being 10 micron, you need what's called a tapered fiber bundle. That is, each of these fiber bundles have a diode laser connected to it. Output of each of these diode lasers gets combined to an output fiber, which gets matched to the end of this double clad fiber. This is a sort of a schematic of how it's done. This is a 6 fiber tapered fiber bundle. This is where the central core has the signal into it. These are the pump. This is the no core pump fibers. This has a core into it, and slowly this gets tapered in this form, and it happens. It works. It works very, very well. Now, what do you do with it? You can make various types of stuff with this. You can make Raman amplifiers, you can make regular amplifiers. The Raman amplifier is a special case that we did work on. The reason I'm moving to Raman amplifiers is because they can operate at very high speed. They can really amplify pulses. There is no limitations. Terbium doped amplifiers can do that too, but Raman amplifier does even higher power. And you use regular fibers associated with it. Conversion efficiencies are very high. Stimulated Raman scattering takes place right in the fiber itself. What do we do with this? What we have done with it, we have studied supercontinuum generation in optical fibers. That is, we take our pulsed source, as I said, mode locked fiber lasers, we amplify it, goes through a fiber or a waveguide, and we get meaning broadband spectrum. That is, a single spectrum like this gets converted into something like this, but the peak power has to be quite high, 1 kilowatts. This is an example of supercontinuum generation in a 15 centimeters long regular fiber. This is the input pulse by half a centimeter, 1 centimeter, 2 centimeters. So it keeps on broadening. And that's how after a while the broadening stops, as you can tell. These may be useful for certain things, such as optical coherence tomography, or just as a phenomena. Certainly optical coherence tomography one can do with it, but there's a lot of hardware as it's done. So things have to be made compact. So this is my next slide. This is the last slide. Summary, I've discussed both semiconductor and mode-locked fiber lasers. Semiconductor lasers are compact. High repetition rate pulses can be generated and have been generated, but it's difficult to get a precise repetition rate. Fiber lasers could be a poor man's workhorse. Certainly in the lab, they're easier to build. Repetition rate can be controlled easily. And they can be stabilized using a feedback loop. And we can use these fiber lasers to study optical communications experiments, optical logic experiments. Optical communications meaning you can put all kinds of signals and study them. You can put digital signals, analog signals, multiplex, hybrid analog and digital together, carrier waves, everything you can study. And then you can do high power, and certainly another arena will be high power pulse amplification and broadband spectral generation. It's certainly feasible in the lab and certainly in the commercial world as well with fiber lasers, because today you can buy fiber lasers that are quite good and quite reasonably stable. Okay, great. Thank you very much for your attention. I'm going to stop sharing. Please feel free to ask questions.
Yeah, thank you, Professor NILOY. You have any questions from the audience?
Yes, sir. Can we ask one question?
Yes.
Sir, is this mode lock have application, LiDAR applications? It means we make a radar. So we can use for LiDAR applications, we can use mode lock lasers.
I think you can. You can certainly do experiments in the laboratory using for LiDAR type applications. There's no questions about it. Whether you can take it to the field, it depends on how stable a mode lock lasers you can build. As I said, today people sell mode lock lasers in boxes. Okay. And so I've certainly seen them in conferences like Leo and OFC. So yes, the answer is yes, you can do it.
And the second question is related to the, as Rashna Madam was telling it, we are working coherent communication. So related to that coherent communication, one my question is there. Can I ask that related to coherent communication?
You may, but I've been away from coherent communications for a long time, so but you can certainly ask. Okay,
sir. My doubt is that in our slides also we have shown that Mach Center modulator lithium niobate Mach-Center modulator. Yeah. So one of the problem that I have also faced, while not in OAK, it in DPSK and QPSK, that when we bias it as a lower MITP point, it could highly fluctuate. It is not stable. So I have done the literature survey that people are using gallium arsenide based Mach-Center modulator. In that fluctuation is not there. So, but the products are not available, and is it really feasible for gallium arsenide?
Gallium arsenide Mach-Center modulators were made in the 80s that British Telecom, not British Telecom, they had a lab that's associated with radar in England. They made Mach-Center modulators back then out of gallium arsenide. Of course, the things have changed now considerably, and people should be able to make much better gallium arsenide modulators. The thing about lithium niobate modulators, they're so used in optical communications these days. You can easily get 10 gigabit and 40 gigabit modulators, but I don't quite know how to answer your questions regarding instability, because for the type of stuff that we do, we don't find that to be the case, but your application may be different. I just do not know.
Okay. Thank you, sir.
Yeah. So any other questions?
Sir, one more question.
Yes, sure.
Sir, just normal in that double clad fiber, Can it be spliced with normal single mode fiber, or some special fibers are used?
Well, if you want to, yes, it can be spliced to normal single mode fiber. The purpose of the double clad fiber is really to get high power.
Yes.
High power into the single mode. That's the purpose. So you have to somehow get power. Double clad fibers come in, is one variety, various varieties. They usually have a regular 10 micron core, followed by one cladding, which is about 100 micron diameter, followed by a third cladding, which is the 300.
125.
Yeah, that's a higher diameter. So you have to match. There's no point putting in a single mode fiber. You can probably splice it, but somehow you have to get, the purpose of it is to increase is to get a lot of pump power into it. For that, you need some sort of a fiber. People generally use this 7 fiber thing, 6 and the central in the middle, or 19 and 6 and central in the middle for this purpose. You can certainly, I think it's possible to splice. Any two fibers can be spliced as long as the outer diameters are the same.
Okay, sir. Okay.
Otherwise, it just wasn't going to splice. I mean, you can try to splice, there's going to be some amount of loss, I guess. Yes.
Okay, sir. Thank you, sir.
So I think Vikas Agarwal had a lot of questions because I think he works for ISRO.
Yes.
Oh, I see.
And he's doing a lot of things in fibers. And I think with that one, I think really we'll conclude this one. I really appreciate the talk given by Professor Nilay that started from fiber, and then he has shown his lab, and he has made what is mode locking and why mode locking is required. Mode lock laser is required for communication purpose. Right from that one, and MZI things which he has shown, and it's a wonderful thing that one. He has also shown a little bit of polyfiber, that is photonic crystal fibers, the application, how it can be used. So there are many applications. I have seen right from the beginning, there were more than nearing 50 participants across India and someone from abroad. And it's a great thing that we could able to hear Professor Niloy's talk. And it's a sort of thing, what is happening in the globe. Sitting in India, we will not be knowing what's happening in US, what's happening in Japan. Of course, if I remember, Professor Niloy will definitely agree with me. Japanese are pioneers in the field of optics. What, Professor Niloy, am I right? I think, okay.
Yes.
Yeah. So based on, so they are actually in very advanced technology. And we have seen panoramic view of Professor Niloy's lab. And of course, here we have seen a lot of research scholars across every nook and corner of India. And they have gained a lot of knowledge because they are working on some fields. So they have got some insight into the fiber and its mode locking and all those things. So with that one, we really, once again, I will thank Professor Niloy for giving a talk sitting from US, from Connecticut University. And also I would like to thank at this point of time many people who are my friends, I think Professor Vishnupal was there, Talabatala Srinivas was there, Dr. M.B. Satyanarayana, then Dr. Gopal Krishna, and Dr. Devendra Mohan, like many have joined today's talk. So even though today is, I think, maybe for some it may be holiday. So and normally this kind of thing, everybody will be on virtual meeting because of pandemic. So with that one, it's a great opportunity for us to host this one from Prakash Bharathi India Group. In fact, this Prakash Bharathi India Group really was started by Professor Naresh Chand, I think close associate of Professor Niloy Datta. And it started like that. So under the banner of the Prakash Bharathi, we are conducting these kind of talks, international conferences like that. And in the coming days, the 24th, we will be having one more talk by Professor Shiv Kumar from McMaster University. Once again, it will be on fiber optic communication. So with that one, Prakash Bharathi under that banner, and we have joined two institutions like Malnad College of Engineering and Calcutta University. So both have joined under the banner of Prakash Bharathi. So our students, especially Rachana, then Yashaswini, Vijay Kumar, Pooja, contributed very well from our institution, and Madhusudan Mishra from Calcutta University. They are huge in number. You can see the participants across the country completely. So with that one, I definitely see there is a lot of thing happening in India, but it needs to happen because we are a little bit far in the field of optics. So now I think whatever I am telling, if I am telling in front of Professor Neela, I was telling for my students, whenever I used to give a talk, this electronics and communication may soon become photonics and communication. Am I right, Professor Neela?
Yes.
Yeah, I think wherever you see this, the last decade was towards electronics. Now photonics is coming, but earlier I think from past 3 decades past, it was just started with photonics. Now photonics is gaining momentum, but unfortunately in India it's very slow, the growth. But of course we are catching with US because of professors like NILOY and others like Vishnupal, then many others who are contributed, and many professors who came from US, they settled in IITs and other institutions. They are giving a lot of good things, and of course we keep going to other countries and they keep coming, and this is a sort of thing we should exchange so that it is beneficial for both our students as well as India. So on behalf of totally the whole India, I really thank Professor Nilay for having given wonderful talk about mode locked lasers. Of course, mode locked lasers need not be in only optical communication, because everywhere we find the application of mode locked lasers. For example, ring resonator you are telling. Then once again, all the optical components, you see the application in medicine, application in metallurgy, application in communication, application in computing. So many things are possible. So with that one, once again, I really appreciate the enthusiasm by Professor Neela, because he has agreed to give a talk. And really, I thank you, Professor Neela. I think
Thank you very much.
finally, I request Madhusudan Mishra to give the concluding remarks from Calcutta University.
Thank you, sir. It was really a nice talk, and I'm glad that it was initiated by you, and now it is at its successful end. So I can see several participants also, like teachers and students. All kind of participants are there in this talk. I hope they all have enjoyed well. And especially thanks to Professor Nilay Datta for giving his valuable time, and especially for us, he took some pictures also, what he usually don't do. And so hope we will have him in future also with some new topics and some new idea, new technology. And I thank all for joining this lecture. Thank you all.
Thank you very much. I really appreciate for inviting me. And looks like quite a few people have joined, and maybe next time we can have more dialogues.
This time, sir, we actually Dr. Naresh couldn't join. He is not available these 2-3 days. So
yeah, he told me. Yeah.
So okay, sir.
Thank you. I really appreciate this, and this is not a difficult time for me to give talk. Like it's pretty. I get up early enough, so there's no.
No, sir. From beginning, we are with you. We are in continuous contact with you, and you are cooperating each time very well. So that's a good thing for us.
Great.
Okay. Thank you, sir.
Okay.
Thank you.
Okay. Thanks, everyone. Anything, Professor Neela? Thank you once again. Shall we